All right, I should be back in business here. All right, we're trying to do triple integral over e of x dv bounded by z equals 0, z equals x plus y plus 5. The cylinder x squared plus y squared equals 4, and the cylinder x squared plus y squared equals 9. All right, so let's try and wrap our heads around this. Right now, I do not care about the integrand. I don't care about x, right? I don't care about this. I'm trying to figure out what E looks like. So what does z equals 0 look like? It's the xy plane, so that's like the ground, right? What is z equals x plus y plus 5? That's a plane, right? And is it above the xy plane? I mean, like at the origin, is it above or is it below? It's above, right? At 0, 0, it's at 5. So I kind of have like a plane on top of the ground. Eventually that plane does cut through the ground, doesn't it? Because it's got an angle to it. So I've got this plane, and then x squared plus y squared equals 4 is a cylinder, radius 2, and it runs parallel to which axis? The z, because z is not in the equation, so z is free. So I've got the beer can, the infinite beer can going up and down, radius 2. Then I have another beer can that's a little bit bigger, goes infinitely up and down, the z-axis, radius 3. So can you kind of visualize what that solid looks like? Got a plane on top, a plane on bottom, and then two cylinders, one inside of the other. So it should be like a shell. It should look something like this. Do you agree? It's a tire that's been stretched, and one side of it is angled. Yeah, it's in bad shape. Okay, so let's now work on what the shadow of this would look like on the ground. So what is the shadow of that solid E? This is E, right? What's the shadow on the ground? Crap. This is the shadow of E. So I have an outer radius and I have an inner radius, right? Terrible drawing. 2 and 3 though, right? 2 and 3. And I want to integrate over that region, right? I want to integrate over that region. So if I want to integrate over that, I look at it and I say that's perfectly suited for polar coordinates. That shadow is perfectly suited, right? So let's talk about some restrictions here. I know that in that two-dimensional shadow of E, I know my theta is between where and where? 0 and 2 pi. I know that my radius is between what? 2 and 3, right? Right? Okay. Now, the only question left is to figure out what z is stuck between. Well, z is stuck between 0 and that plane. Now, the plane equation up there was x plus y plus 5, wasn't it? So what do we still have to do here? Change the x's and y's to r cosine theta, r sine theta. So instead of using that, I'm going to use z is between 0 and r cosine theta plus r sine theta plus 5. Y'all with me? And now I'm ready to set up my triple integral. I have triple. I go first my theta, 0 to 2 pi My r goes from 2 to 3. My z goes from 0 to r cosine theta plus r sine theta plus 5. And then what was my integrand? It was x, wasn't it? But x has to be converted from Cartesian to polar or cylindrical. We can say polar and cylindrical kind of synonymously as long as we understand that we're talking about the x and y part of it, right? That gets switched. So we have what? R cosine theta. R, good, don't forget the r. And then dz, dr, d theta. Now, I'm not going to work through this whole integral, but let's talk about the first integral you would do. You have to do the dz, right? So what's the antiderivative of all this stuff with respect to z? R squared cosine theta z. And then you're going to evaluate that from z equals 0 to z equals that. Figure out what that is, and then integrate that with respect to r. Then replacing r with 2 and 3, integrate that with respect to theta, and then replace theta with 0 and 2 pi. Yes? Okay. I won't work through that. Now let's take a look at this. Oh, I do it. I'd probably had Mathematica do it, right? All right, so here it is. Here's our beer can with the beer can inside. There are 2 planes, right? And I can show it, but then I have to pull everything else out. That's it. It's a tire. It looks like a tire. Yeah, so there's the setup. And the antiderivative, let's see, when you do the antiderivative with respect to z first and plug in those 2 pieces, you get that. Can you integrate that with respect to r? Pretty easily, right? Because all the cosine t stuff, that's all constants, so you just integrate. And then this one right here, we integrate with respect to t, or theta. T is theta for me here. And cosine squared, that's a double angle. I mean, sorry, that's a power reducing. You can turn that into, what, 1 cosine squared t can turn into 1/2 plus 1/2 cosine 2t. And then this one right here is a basic substitution. Anyways, you do all that, you plug in 0, 2 pi, you get 65 pi over 4. Let's look at example 2. So when do you think cylindrical is going to come into play? When you've got cylinders, right? I mean, that's the thing that's going to kind of clue you in, right? You've got cylinders. Maybe cylindrical coordinates is what I should use. Do you see why using Cartesian coordinates probably wouldn't be nice here? Because that shadow wasn't a Cartesian rectangle or anything. So we want to go to the coordinate system that makes most sense for the problem. Find the volume of the solid between the cylinders. X squared plus y squared equals 4. X squared plus y squared equals 16, which also lies within the sphere. X squared plus y squared plus z squared equals 36. I kind of wish that I didn't have the picture there for you, because part of this is you being able to visualize it without anything. You've got your 2 beer cans again, right? Running parallel to the z-axis. And then you got radius on those is 2 and 4, right? And then you've got a sphere. So you've got to be able to visualize, and the sphere has radius what? 6. You've got to be able to visualize that the part that's bounded by all of those curves. And that's that inner part here, which is a pretty cool looking shape, actually. And it's really hard to make out the contrast there where the edge of that is, isn't it? Wonder if it's better when it's all dark in here. You can kind of make it out a little bit more. Do you see it, like right in here? Do you see that? That's part of the sphere. If I bring it in a little bit, it'll probably, that helps maybe a little bit. Okay, so looking at this thing from the top, the shadow of the region we're talking about, right, is again polar. So example 2, I'm not going to write the whole thing out. We have radius was 2. We had radius was 4. This is the shadow, right? Shadow of E. Here's our region all in here. So what is our restriction on theta? 0 to pi, r, 2 to 4, z. Ooh. What's that? It's the sphere, but what's the problem here? What's the problem that we're going to run into? If you try and solve the sphere equation for z, you get plus or minus. That's right. Why don't we, instead of trying to find the volume of the whole thing, or not the volume, instead of talking about the whole thing, why don't we double it? Do you all agree with that? Yeah, let me do something real quick though. Could we do it all at one time? If I solve that for z, that equation, I know we could double, but if I solve it for z, do you agree I get this? Square root, plus or minus, sorry, square root of 36 minus x squared minus y squared. And because we are going to be in cylindrical coordinates, we know x squared plus y squared is r squared. So this becomes plus or minus square root of 36 what? Minus r squared, right? Because we had a negative we factor out. So couldn't you look at the positive one as being the top function and the negative one as being the bottom? You could, right? You know what I'm saying? Instead of going from 0 to the top and doubling, I could just do the negative on bottom, positive on top, which is what I'm going to choose to do. So my z is actually between negative square root 36 minus r squared to positive root 36 minus r squared. Now, what is the function that I'm integrating? Oh, I didn't ask. Oh, I didn't even ask for it. Sorry, I'm confusing you now. How do we, if we want to, don't we want to know this volume in here, right? But I'm treating that, that's my region, E, right? What triple integral gives you the volume of E? If you integrate 1, right? So see, I don't have an f of x, y, z for this problem. So what I'm trying to do is I'm trying to find the triple integral over E of 1 dv. Do you understand what I'm saying? I don't have a function. So this becomes 0 to 2 pi, 2 to 4, and then negative root 36 minus r squared, positive root 36 minus r squared of 1, and then what? We are in cylindrical coordinates, right? Which means we have to include that r. So times r d z d r d theta. See how that's going to work? So the important thing here is to remember that you're going to have an r in there. And also, because it's triple integral, you've got to have 3 differentials. You've got to have dz, dr, and d theta. Then you would have had to double it, yes. But you also could have done this problem as a double integral and just done it in polar. What would that have looked like as a double integral? Well, I would have gone 2 times 0 to 2 pi, 2 to 4, and then all I need is the top one. The top one is square root of 36 minus r squared. Then I have r dr d theta. That's what it would have looked like as a double integral. Well, would it? Let's see. What's the antiderivative of 1 with respect to z? It would be rz, right? Okay, plug this in for z, and you get the square root of all this stuff times r, and then subtract the same thing, but subtract the negative. That's going to double it, isn't it? So you're going to get 2 of them, and so you wind up being at the exact same place. So there are ways that you can do double integrals with triple integrals. They get you to the same place in this. In this case, they get you to the same exact place. In fact, you might argue that double integral is a little shorter. It will always become a double integral, yes. Will it be geometrically the same exact thing? I think that will depend on what you're integrating. The good part of this is that these are constants. That's what's making this nice. These are constants. All right, do I work that one? Well, I don't work it. Mathematica worked it. And you get 383.595. So there's a homework assignment for this section. Pretty short, right? I mean, 3 problems. The only thing that I want to know when it comes to the cylindrical is that you're just comfortable when you see the right type of region, when it's just the perfect type of E, you know that you can go to cylindrical. Questions? Well, now let's talk about then spherical coordinates. Yeah, I didn't really think too much about it. I was contemplating whether or not I should go through those integrals, but I think everyone's okay. Is that too much to assume? All right. Let's try and open up here 12.7. We're going to do 12.7 today. Yeah, I think we'll be a little bit ahead. I mean, we may even see 12.8 today. 12.7 and 12.8, I'm not quite sure why it gave us so much time. I think what happened is once I got to about 12.5, when I was making the schedule, I was like, I'm trying to give us 1 day for each. And that way, I don't fall behind at the end. Trust me, if we can be ahead a little bit, that's a good thing. All right, here we go. Triple integrals and spherical coordinates. So this is just what I was saying a second ago. We have not seen this, all right? Cylindrical coordinates, we're able to just basically adapt what we already knew about polar, right? The only difference was that the z was z, right? Nothing else. Spherical, completely different, all right? If I'm going to try and get to that air conditioning vent, is that a return? I don't know what that is. Doesn't matter. So if I'm trying to get there, I could go x, I could go y, and I could go z, or I could go theta, r, and then z, right? Or now what I could do is, like I said, I'm actually standing at the origin pointing straight up. And you tell me theta turns, and then what are we going to use for our next angle? What's that right there? Phi or phi. I've heard it said different ways. So now you go and now you turn, or you rotate a certain angle towards the point. Then you walk out a certain radius, but we're not going to call it r because we don't want to confuse it with r in polar, so we call it rho. That's rho, all right? That's right. It's just kind of to get us away from thinking we're in cylindrical. Now look at these conversions from Cartesian to spherical. They're not as clean and easy as the conversion from Cartesian to polar, or Cartesian to cylindrical. Anywhere we see an x, we have to replace it with rho cosine theta sine phi. Y has to be replaced with rho sine theta sine phi. Z is rho cosine phi. Is it okay if I say phi? All right. And then what's rho squared? Is x squared plus y squared plus z squared. Right? And that's the idea of a sphere. Right? The sphere, this is basically a sphere centered at the origin, radius rho. With me? Now, the reason we call it spherical is because if I fix a radius, okay, if I fix some radius, and I start letting theta swing around, right, and I start letting phi change, then what I do is I create parts of a sphere. It's kind of like if you have, imagine me standing here with a rope with a ball on the end of it, right? And I'm allowed to change the angle of that rope, but I have to keep the rope the same length. And I start swinging that thing all around me, right? It's going to trace all these paths out around me, but all those paths will lie on a sphere. Yes? Same distance from me. So I create a sphere. What would be kind of a neat exercise for you, and why don't I offer it as a bonus problem to you? I'm sure you probably Google it, so it's not even fair. Is to show that these conversions are true. Like, how did we show polar conversions were true? Do you remember how we showed the polar conversions? For polar, all we said was, look, if we're on a circle and we want to get to this point, right? We said that that point has an x and has a y. There's an angle and there's a radius. And from that picture alone, you get all the formulas, don't you? X squared plus y squared is r squared. Arctangent of theta is y over x. X is equal to r cosine theta. Y is equal to r sine theta. So you can get it all from there. I offer you as a bonus to do a similar construction for the conversions from Cartesian to spherical. Understand? So show with some pictures that x is going to be equal to rho cosine theta sine phi, that y is going to be equal to rho sine theta sine phi, and that z is going to be equal to rho cosine phi, and that rho squared is equal to x squared plus y squared plus z squared. What do we think? Do next time with your mini exam? Okay. That's what we'll do. For bonus. Now let's talk about what these regions look like in three-dimensional space. So triple integrals with spherical coordinates. For region E, where our theta is between alpha and beta, so theta is my turn right here, like this, right? If I fix that turn between two constants, and then I let my phi be between two constants, so I'm turning like this, and then this is allowed to go between two constants, right? So let's see if I can do that one time. That's kind of hard. You get what I'm saying, right? Then what am I drawing? If my radius is fixed, what am I drawing if I'm swinging back and forth like this, but then I'm also changing this up and down? What am I drawing out there? What does it look like? It's like a rectangle on a sphere, though, right? So it's like a curve. And then, what if I allow my rho to go between two constants? So not only am I swinging between two constants this way and changing this back and forth this way, my rho is going back and forth this way between two constants. You get a region in spherical coordinates. Now, I have a picture. No, I thought I did. Where's my spherical region? I didn't make a code. I didn't code this up. What? No. You got to be kidding me. Well, that's just not fair, man. That ain't right. I've got to fix that. Well, here's an example, okay? If someone codes that up for me in Mathematica, I'll give you bonus points. There's an example. That's kind of a tough way to see it, but check this out. Theta is between here 0 and what? Pi over 2. So I'm going like this, going 0 to pi over 2, 0 to pi over 2, right? My phi starts here and it goes from here down to the x-axis. So my phi goes from what? 0 to pi over 2. It's the measurement of this angle, okay? 0 to pi over 2. And then what does it look like my rho is going between? 4 to 9. Yeah, this is a 4 right here. So do you see what it creates? It looks like a cantaloupe, right? A piece of cantaloupe that's been cut, so it's got kind of like a little hollow center to it, but it's curved. You all see it? Okay, that is what a, do you remember in the first triple integral we did, the first region in triple integrals were boxes, weren't they? X between two constants, Y between two constants, Z between two constants, and we got like a shoebox, right? That's what a box looks like in Cartesian, because X, Y, and Z are all between two constants. If you go to spherical and you let your theta, phi, and rho be between constants, this is what it looks like. So this is almost like a box. This is a spherical box, if that makes any sense. And spherical coordinates, that's what a box looks like when you're... Do y'all know what I'm saying or not? Because when we talked about polar, we said there's a difference between a polar rectangle and a Cartesian rectangle. Polar rectangles look like polar sectors. What looks similar to polar? Like if you're looking straight down, like this? Is that what you're saying? What's different, though? Because I would agree with you that this right here and this right here, right, looks kind of polar. But see, what's the shadow of this? What does the shadow of this thing on the ground look like? It's the whole half circle, right, or quarter circle. Okay, well, let's not get too wrapped up in trying to connect it to cylindricals so much. That's what a spherical rectangle looks like, basically. So let me go back to our formula here. If theta is between alpha beta, phi is between C and D, rho is between A and B, then we have a triple integral. The outer integral goes from alpha to beta, and that's the differential is d theta. The middle integral goes from C to D. That's our restriction on phi. So we have the middle integral is d phi. And then our inner integral goes from A to B, and that's our restriction on rho. Now look at this. F of all this crap, all this crap, all this crap. But what is rho cosine theta sine phi? X here, Y here, Z. What the hell is this? Rho squared sine phi. Well, you remember when we did polar, we had to account for that R? Said you always have to put R in the formula, right? Well, guess what? Anytime you use spherical coordinates, you always have to put a rho squared sine phi. And I think your question is probably going to be why, right? Maybe. Next section. Next section. Not yet. We'll see that. We'll see. This is what's going to pop out of here later on when what we do is what's called a change of variables. So we are changing our variables here from x, y, z to theta, phi, rho. Anytime you change from one variable to another set of variables, you have to somehow account for it in here. What section was polar? 12.3? I want you to see, because it's been so long, how we came up with that thing. Here was the picture. See if you remember this. I was trying to explain in double integrals where dA was just the dx dy, and that's Cartesian. And then we're saying, but in polar, the rectangle looks like this. And I tried to explain that our dA here was the red, and so this length on one side was dr, our change in radius, and this side right here was an arc length. And the arc length formula, right, arc length was S equals r theta. So r here was the radius, and our actual angle was our d theta, so that was where we got that. So that's why we said when we multiplied the dr times the r d theta, that r popped in. Yes? It's much more challenging to show this for spherical. Much more challenging. So the next section is going to give us a way of doing it pretty much for any change of variable, whether or not it be polar or cylindrical or Cartesian. Cartesian. Anything from any system to another. You want to change your variables, that's fine. Something might pop into that integral. We'll be able to figure out what it is. We just don't have it yet. That's right. I guess my whole point of showing this to you is just to remind you that the way I showed it to you was geometrically. The next section, we're going to have a way of getting it algebraically instead. Yeah, this right here is, well, yeah. All right, let's do this one here. So find the triple integral over E of e to the square root x squared plus y squared plus z squared dv, where E is the region in the first octant between the spheres with radius 4 and 9. Yeah, that's E, the exponential function up there. So I'm trying to do triple e to the square root x squared plus y squared plus z squared dv. Now what we're going to try and do is do spherical coordinates, because they told me that my region is between two spheres, right? Spheres, I'm thinking spherical. So what are the two spheres that they're talking about there? What are the radius 4 and 9? So I know that if I'm in the first octant, then I only swing between where and where? On theta, it's got to go between 0 to pi over 2. And then phi is my, not down to up, it's actually up to down, but it's the same thing here, right? Still goes from 0 to 2 pi. Or sorry, 0 to 2 pi, 0 pi over 2. And then what else do I have to look at? My rho is going to be between, what? 4 and 9. Now let's look inside the integrand. This is the function I'm trying to integrate, right? Now what am I supposed to replace all my x's with? Rho cosine theta sine phi, and then all my y's get replaced with something, and all my z's get replaced with something. However, one of the conversions from Cartesian to spherical is that x squared plus y squared plus z squared equals rho squared. So x squared plus y squared plus z squared, that actually equals rho squared, so that's the square root of rho squared, which is just rho. So this triple integral actually becomes e to the rho. Oh, you know what, I'll come back to that. Let's get the limits on here. 0 to pi over 2, 0 to pi over 2, 4 to 9, Now my e to the rho. And then because I've converted over to spherical, I must include rho squared sine phi. D, D, D. What is it? D rho, D phi, D theta. So if I'm going to integrate this with respect to rho first, right? What am I going to have to do to get that integral right there on e to the rho squared? Integration by parts, you'll probably have to apply it twice, right? What's that? Oh, go off a table, you mean? I know what you're saying. Yes, there are different ways that it's taught where you can kind of go through the integration by parts quickly, right? Several times. So you do that, but you use integration by parts. And then once you get that, right, you plug in 9 and 4 for rho, and now you'll integrate that with respect to phi. When you do that, you're basically going to have a constant in front of sine of phi. The antiderivative of sine of phi is negative cosine phi, so you do that, and then you plug in 0 pi over 2, antiderivative with respect to theta, do all that, blah, 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 and you should get, well, that's the exact answer, I suppose. 65 e to the 9th pi over 2 minus 5 e to the 4th pi, which I guess the answer, whoa, the answer is pretty large. 826,482. Is that the volume of that thing? Is it the volume of that solid? Well, did we integrate 1? No, we didn't integrate 1, did we? We integrated what? E to the rho, right? E to the rho is what we integrated. So this was where that thing, you had to be careful that the solid is what we're integrating over. Because we're integrating some function, then this number really represents, well, we don't really know because it depends on, you know, if we've associated this function with some physical quantity or something. This is just the value of the triple integral. If we did, however, replace the e to the rho with the constant 1 function, then that would be the volume of that piece, which would have been much easier to get without doing calculus, right? Yeah, we just find the volume of a sphere, subtract the volume of the smaller sphere, cut it into 8 equal pieces, and take one of those 8. But that's the way you would do it if that's what you wanted the volume of, right? It's not a volume. And so there's only 2 problems out of that for you to look at. All right. Take a quick, just like a 1-minute stretch. I never turned the lights back on. I don't know why I didn't do that. 1-minute stretch. I'll be right back. Oh, man, I'm so thirsty. Chapter 13, yeah. That's where we're headed. That's what I want to be able to spend a lot of time on. That's it. Yep. One of the main results. And it's very difficult right now to explain because we have to first, the thing that makes chapter 13 hard is we have to first develop, the whole idea of what a vector field is. Once we understand what a vector field is, then what does it mean to have a path through a vector field? So there's too much development that has to happen before we can actually get to it. Yeah, well, Green's theorem, you know how like when you were learning areas, you did like Riemann sums, and then at some point you were given the fundamental theorem of calculus, which it just works, right? You find the antiderivative, you plug in 2 points, and you have the value of the area. The Green's theorem is similar to that in the sense that you can do some really hard things that were hard earlier, very simply later. Yes. Honestly, the thing that's going to be most challenging in Chapter 13 is just sorting out what it is that's being asked and applying the right formula to what's being asked. And that's really what 13 is going to come down to, because there's lots of formulas in 13. Lots and lots. All right, we ready? I wasn't ready to start 12.8 today, but I think what I'll do is at least intro it. I definitely don't want to work through the whole section, all right? Because you'll have enough homework to do when you have got your mini exam. Now you have a bonus problem. And apparently, some people need to get caught up on homework too, right? Okay. So let's, I did send out the homework assignment for 12.4, 12.5, I think, last night, or the day before. All right, change of variables. Change of variables. All right, remember that when we were looking at a double integral over some region D in 12.3, which was polar, what we did is we made these substitutions. We said, look, everywhere we see an x, we're going to replace it with r cosine theta. Everywhere we see a y, we're going to replace it with r sine theta. And that came off of the right triangle, didn't it? So for the sake of us being able to understand what's going to go on in this section, instead of me using the variables r and theta, let me use u and v instead. Right? So let's just say we started chapter 12, section 13 over, and I said everywhere we see an x, we're going to replace it with u cosine v, and everywhere we see a y, we're going to replace it with u sine v. It's the same change, isn't it? Just different dummy variables. More generally speaking, we have made the substitution that x, okay, x can be determined if you give me a u and a v, right? You give me u, you give me v, I can tell you what x is. Therefore, x is a function of 2 variables. Yes? And y, since y depends on u and v, y is a function of 2 variables, right? Right there. Y, if you give me u, you give me v, I tell you y. So y is a function of u and v. Yes? With this in mind, let's see what happens to a polar region in the xy plane under this transformation. Think of what I'm about to do here. I want to see what happens if I start with a polar region and I switch it over to Cartesian. What happens? All right, so this is really complicated. I tried my best to make an animation that would make this make sense, and I think I'm going to kill the lights for it. All right. This was a polar rectangle, wasn't it? This polar rectangle came from a rectangle in Cartesian. So we take a rectangular region in Cartesian, we convert it over to a rectangular region in polar, right? And that's the conversion. This is what it looks like in polar, that's what it looks like in Cartesian. What I want you to see, though, is you see that green arc right there? That green arc corresponds to this side of the rectangle. So what I'm going to do here is I'm going to change, nope, crap, go back. I'm going to change my theta. So I'm going to make theta jump. When I make theta jump, look what happens over here. I made my theta change from here to here, right? And it jumped from that corner to that corner, which means that that side of this rectangle corresponds to this arc of the polar region. If I change my radius, and let me bring the polar one back. My radius, here we're starting at this point, if I change my radius and jump out that way, it goes across that black line. You see it jump across there? Straight across. So this side right here of the polar region corresponds to that side of the rectangle. Yes? So what about a point in here? A point in there should be somewhere in between. Now I'm going to have to grab this. Let me see if I can. I can't. Change my radius over here. I'm here. Change my radius. I'm here. If I change it again, I'm out here. Do you see me out here? Okay. Let me zoom out. I don't remember what this was. I'm trying to remember what all this was. There's a better, that's probably better. I should have brought that, take that red one out of there. Y'all see all that? All right. Now, let's look at this picture. This is a vector. You see the vector? And you see this vector. Why do I have change in V, R sub V? What is that? And then what is this one, change in U, R sub U? I'm going to come to this and then I'll go back to the picture. We can see that our strange region in the UV plane, which is the polar region, becomes a rectangle in the XY plane. We still need to determine how the area of region D in the XY plane is related to the rectangle S in the UV plane. So I've called the D region in Cartesian. In Cartesian, I've called it D. In the polar, I called it S. Now, it can be shown, all right, it can be shown that R of UV equals X UV, Y UV. So R of UV should be like a surface, shouldn't it? Do you agree? R of UV? Or no, not a surface. This is a vector function. It's a curve. Do y'all see the vector? R of UV. And it has two components to the vector function, doesn't it? So what it draws is it draws a surface with vectors. And because our third component is 0, that means it doesn't come out at us. So it lives in two-dimensional space. But look at where these components of the vector function come from. Wasn't that the transformation that we made, right? So I put in here, I'm waving my hands. It is somewhat difficult to understand. If you want to talk about it more seriously, come by my office because it's hard to explain why that's true. But let's just take it on faith for right now. So what's the area of that region? What's the area? Well, remember the parallelogram rule? That if you have two vectors, then the area of the parallelogram formed by those vectors is the magnitude of the cross product of the vectors. Yes? So C notes on parallelogram. And that this is the property I'm using. The area is the cross product of the vectors, and then this right here, look at this, delta U delta V comes back from that picture. Look, delta V is a scalar, this is a vector. This is a scalar, this is a vector. So if I want to cross those two, the scalars can come out and I can cross just the vectors. That's a property of cross products. So go back to this now. And then if I actually do this cross product, and remember this was like the first way we ever did cross products, then you get this. It yields the vector 0, 0, and then this. Remember, if you have two vectors that live in a plane and you take their cross product, the cross product is perpendicular, so it should come out at the z, which is why we get 0, 0 here. And this right here is partial of x with respect to u, partial of y with respect to v, minus partial of x with respect to v, times partial of y with respect to u. So what we get is this cross product is equal to this. Finally, letting the number of parallelograms go to infinity, then what we do is we change this double integral to first switching the x and y's over to what they were, right? X is now a function of u and v, y is now a function of u and v, and then my dA switches over to this. And that's what we just got when we did the cross product. Do y'all see that this last piece over here is just a way of us computing the area of that? And when we go to infinity, what happens is when we go to infinity, they get smaller. And do you see how that rectangle, the dotted rectangle, approximates that better and better and better? I'm just trying to get you to see geometrically a little bit why it is that when we change variables, you're free to do so, but your new integral, you'll have to switch the variables in the function, and then you have to, of course, your differentials change, right? Because you had x and y, now they become u and v, but there's something that has to go out there in front. And the thing that goes out there in front is this piece. And that is known as the Jacobian or the Jacobian Determinant. That right there. It's called the Jacobian or the Jacobian Determinant. And I reference you to a page in the book. Let's see if that's still accurate, because this is a different book. Yeah, it's still on page 746. So there are some conditions where this won't work, certain changes of variable, but I'm not going to get into them because I won't ever give you something like that. Now, they call it the Jacobian Determinant for a reason. Remember what a determinant is. For those of you who've taken some linear algebra, right? If someone gives you a matrix A, B, C, D, right? This is a matrix. The determinant is equal to what? A, D minus BC, right? That's a determinant. Well, for us, if you look at that formula we have, where is it? Let me write it down. This is what we have. We have partial x with respect to u times partial y with respect to v minus partial x with respect to v times partial y with respect to u, right? That can be looked at as the determinant of partial x with respect to u, partial x with respect to v, partial, God, my thing's acting weird. Partial y with respect to u, partial y with respect to v. Do y'all see that if I say, hey, take this right here and give me the determinant, you would go this times this minus this times this? And that's this formula, right? So it turns out that the determinant of that is really going to help us get that little kind of that cross product. All right. Here we go. I'm trying. This is the kind of last thing. I'm not going to do any examples or anything today. This is the last thing we're going to do. Let's take a look at this right here. When we had this integral over d of f of xy dA, and this was in Cartesian, I came in here and I made a substitution, didn't I? To go to polar, I said x was equal to r cosine theta, y was equal to r sine theta. Yes? Now, because I want to, I'll give you the option here. Do you want to stick with r and theta, or do you want to switch to u and v so it matches the formula? I don't care. R theta? Good. We'll go with r theta. We'll go with r theta because I wanted to make sure you can do more than just follow the formula, that you know what the pieces of the formula, where they come from. So x now is actually a function of what two things? R and theta instead of u and v, right? And y is now a function of r and theta also, right? So if I'm going to make a change of variable, and that's the change I'm going to make, right? X is r cosine theta, y is r sine theta. Then my double integral over my new region, which I will call S, is equal to f of x of r theta, y of r theta. You tell me. I'm looking at the formula that I have boxed there. Okay, which is then times the magnitude of partial x with respect to, here for us it would be what? R times partial y with respect to theta minus partial x with respect to theta times partial y with respect to r, and then d r d theta. Do you all see how that's just that boxed formula? Do you all see it? Okay, now let's talk about these things. What is the partial of x with respect to r? Well, what is x? X is r cosine theta, right? So what's the partial of x with respect to r? So that means you treat what like a constant? Cosine theta is like a constant. So what's the derivative of r times a constant? No, that's antiderivative. It's just cosine theta, isn't it? So this is just cosine theta. And then what's the partial of y with respect to theta? I'm doing these two pieces right here. What's partial of y with respect to theta? Well, theta's inside the sign, right? R is a constant. What's the derivative of sine of theta? Cosine theta, but then there's an r in front of it, right? So this is r cosine theta. Y'all agree? Okay, what is, I'll do it next to it, what's the partial of x with respect to theta? So I'm now doing this part right here. Negative, what is it? Negative r sine theta. And what is the partial of y with respect to r? Sine theta? Correct? All right, so this is now going to become double integral over s, f of, now x of r theta is actually just r cosine theta, isn't it? Y of r theta is actually r sine theta. And then when I do this right here, it's the absolute value of partial x with respect to r, which was partial x, hold on, partial, do y'all want to go ahead and multiply them now? Okay, it's the two red ones, right? So it's r cosine squared, god damn, what's wrong with this thing? Cosine squared theta, and then I have minus, these two multiply, but these two multiplied are negative r sine squared theta. So it becomes plus r sine squared theta. And then dr d theta, right? But if I factor an r out of both of these, I get cosine squared theta plus sine squared theta, which is 1, which leaves me with the absolute value of r, and the absolute value of r is r, and that's why you have to have the r when you go from Cartesian to polar. Understand? The Jacobian determinant is awesome because what it allows you to do is you can go from any coordinate system to any new coordinate system that you make up on your own. Like, I mean, there's nothing wrong with me walking in here and saying x is going to be equal to a function of two things, right? Now, I chose r and cosine theta because that matches up to a nice geometric picture, right? Right triangle, everything was great. But I could make up my own change of variables. I could just make it up. All right? I can make up what my y is as long as it's a function of the same two variables. If I do that, I'm allowed to switch everything over to this new coordinate system, this new change, as long as I convert my integral over like this. Okay? Now, what happens when you go from two-dimensional to three-dimensional? Well, I'm skipping my example here. Skipping a couple, we'll get back. Oh, do I not do triple? Oh, I don't do triple. That's a shame. I thought I did. I spared you triples. I don't know, I spared you triples. I might edit these notes, sorry. Because if you have a triple integral and you want to do a change of variables, like you want to go from Cartesian to spherical, what did we get when we popped that spherical, when we went to spherical? What had to be in the integral? Rho squared sine phi, right? Well, that's because we did a change of variable. X was equal to now a function of what? Theta, phi, and rho, right? And y was a function of theta, phi, and rho, and z was a function of theta, phi, and rho. So what would happen is that you now have to look at what's the Jacobian determinant when you have three functions. So now you get into determinants of higher order matrices, which the determinant of a 2 by 2 is easy, but the determinant of a 3 by 3 is more complicated, right? For those linear algebra people. I mean, it's just more complicated, that's all. So I might have to revisit that. I'm out of time, unfortunately. I know. There's no homework from this. But hold on, I still have 3 minutes. Hold on, just y'all can stand and watch this. Look at this. Look at this right here. I want to integrate. This is my double integral. D is the region above the x-axis bounded by these two. Right? So here it is, right here. And I want to make a change of variables. X is this and y is this. So why in the hell would you ever do this as a change of variable? I don't know. I mean, we do know, but I act like we don't know right now. Okay, that's not polar, right? We're not making a polar switch or anything like that. It's just some crazy switch. And when we do that, look what happens. We basically turn rectangular into this, and then the integral, the actual integral, will change, and we have to do Jacobian determinant. And sometimes when you do this change of variable, a complicated integral that you couldn't figure out before becomes easy. And that's a great thing. Yeah, I just have to stop at some point. This would be very difficult to integrate. All right, that would be a tough thing to integrate necessarily right off the bat. It would take a little bit of work. But if we do a certain change of variable, then we'll be able to integrate that a lot easier. We'll spend a lot of time on that next class. We'll spend the entire next class on this section. Now you can go. Have a good day.